Hello everyone, this is Mr. Jackson and welcome to Chemistry A. Today we're going to discuss isotopes and ions, okay? Really simple. What is an isotope? An isotope is the same element but it has different amounts of neutrons. So here we have carbon isotopes. Here we have a carbon. We know it's carbon because carbon has the atomic number 6, which means it has to have 6 protons in their nucleus. So this is carbon. But it also has 6 electrons to balance it. Every neutral atom always has the same exact amount of electrons in its shells or cloud to balance it. And so here we have 6 electrons as well, but it's the protons that make it carbon, okay? But carbon can actually have different amounts of neutrons. Now the most common one is one with 6 neutrons. Because if you look in the periodic table, the average weight of all the isotopes is 12.01, which means the most common isotope or state of carbon is one with 6 neutrons. But if you've ever heard of dating dinosaur bones and old things like that in fossils, they use what's called carbon-14 dating. Carbon-14 is a carbon atom that has 14 nuclear particles, and 6 plus 8 is 14. Here, 6 plus 6 is 12. So when carbon-14 increases in a fossil or a soil sample, that means it's older. So carbon-14 can be naturally found, and so when you take these two and you start to look at how much is in a soil sample or whatever, then the carbon-14 tends to start to pull the weight of carbon from 12 up a little higher. But there's not that much carbon-14 naturally found, but it does affect the weight overall. So what we have is we have the same element, but just one is heavier than another, okay? That's an isotope. Almost all atoms, to some extent, have different isotopes, meaning they have different amounts of neutrons. Does that change their chemical behavior? No, they behave chemically the same. It just happens to have more neutrons. They have not discovered any impact from those neutrons of changing their chemical behavior. So whether you have more or less neutrons, it is still going to chemically behave as carbon no matter what. Okay? Well, what particle never changes? Well, we just told you that. The proton. It's the identifier. So it is okay that these neutrons change, but we have to make sure that the protons, which identify the element, never change. So if we could change the protons, we can actually create a new element. And they do that in particle accelerators, but we don't do that in everyday chemistry. When you eat food, when you cook food, when you burn stuff in the fire, no matter what, everyday chemistry does not change the number of protons. Elements do not change. That takes too much energy to change the nucleus. Okay? So it is the protons, but then we can change the neutrons, which makes it a different isotope, but the same material. We have a symbol that we can use to show you that. What you do is you take the chemical symbol and you put it in the center. So let's take our chemical symbol. Here it is carbon. So we're going to put it in the center. Carbon here and carbon here. Okay? But what we do is we then put its atomic number from the periodic table, and that's the proton number, and we put it down in the bottom left-hand corner. So carbon, to prove it's carbon, we always leave those numbers 6s so we know it's carbon. But to show you it's a different isotope, we change what's called the mass number. The mass number is the protons plus a neutron in that particular atom. So 6 plus 6 is 12, so this would be called carbon-12. Okay? And 6 plus 8 is 14. This is called carbon-14. So if you were looking for carbon-14 dating in an old dinosaur fossil, you'd try to see how much that is at present. Okay? So these are the same element, but one has more neutrons, so its total atomic mass number has gone up. Okay? This is not the average mass you find in the periodic table right here. It is actually just the mass of the 2 particles in the nucleus at that time. Okay? So that is called the isotope symbol. Okay? And this is the mass, called the mass number. And this one right here is called the atomic number, which is from the periodic table. Okay? So you need to know those 2 things. And let's go on from there. So we have that symbol, and it's easy to figure out. So I'm going to go down, and that's what an isotope is, and I think that's pretty much enough information. So remember, it's just a heavier atom, but there's multiple of them. And some atoms actually have 5 to 6 different isotopes. Iron can have, I think, up to 7, but I know there is iron. If you look at iron right here, iron is number 26, and it has a 55.8. So 56 is the most common iron. So there is iron 56, and we would put a number 26 down here at the bottom because that identifies it as iron. But there is also iron 54, which causes the number to be pulled down from 56 down to 55.8 right here. So that means there's more of that found too, pulling the average down. Okay? There is also iron 58, which is very common too, and these are ones that are more rare, though, in a sense that they actually are found more in isotopes are found more in less samples, or not as much. Okay, so there's an example of 3 isotopes of iron. Okay, let's move on. Let's talk about ions. Ions are very simple. An ion is an atom that has lost or gained electrons. So let's stop for a minute and look at our Bohr diagrams again. Here I have sodium. Sodium has 11 protons. So in its neutral state, it has to have 11 electrons. So 1, 2 on the first energy level, which is limited by the Bohr diagram. The second level can hold up to 8. So 2, 4, 6, 8. Plus 2 is 10. So it must have 1 more in the third energy level. These outer levels around any atom is called a valence shell. So the valence shell is the outermost level on any atom. Okay? The inner ones are called the kernel, but this valence shell idea will come back quite a bit, so I want to keep that in mind. Okay? So we're talking about atoms, and we're talking about how they can become an ion. It's a charged atom. So ions are charged atoms. And they get charged by becoming positive or negative. Let's talk how that happens. Okay, on the periodic table, if you go to the noble gases, which are here in the very far right-hand column, okay, and that family is called the noble gases. They are very stable elements, okay, and they found that if an element can get the same number of valence or outer shell electrons as a noble gas, it stabilizes. It's just something that's very stable to elements. So all the elements in the periodic table a lot of times are competing to have an outer electron shell like a noble gas. Hydrogen would love to be like helium. So would lithium. Okay, sodium would love to be like neon, and so would fluorine. And so what they do is they actually are willing to let go or pick up electrons to be like a noble gas. And if you think about this, electrons are around every atom, and they're very easy to remove and add to them. Just think about walking through your house on the carpet with socks, and you walk through the house, and then you grab the door handle, and you get a shock. That's because you have scraped electrons off the atoms in the carpet. Electrons are very easy to get to move, okay? And it's not hard to make electrons move. But an atom that has gained or lost electrons, then they're going to become charged, and we call those charged atoms ions. So let's look at sodium for a minute. Sodium has a valence shell with 1 extra electron. If it could lose that 1 extra electron, see it has number 11 right here, it has 11 electrons because it also has 11 protons. If it could lose that 1, it would now have 10 electrons, which would act like neon. So sodium is very willing to give its electrons away in the outer shell. Then that shell disappears, and now it has 10 electrons. It has 8 in its outer shell, and it feels very stable. So sodium would love to give away an electron, but that would make it positive because it has now more protons than electrons, so we would write it this way and put a little 1 there. And sometimes they put the number on the left side of the positive sign. I put it on the right. It doesn't make a difference, but that means sodium would love to give away an electron, okay? And so it could be a positive ion in some cases. Well, fluorine is just the opposite a little bit. It has 9 electrons. If it could get 10 by gaining an electron, then it could act like neon. And so fluorine is a taker of electrons from other elements, trying to be like a noble gas. And so it wants 8 in its outer shell, because 1, 2, 3, 4, 5, 6, 7, 8 would make it feel like neon. So here you see it has 9 electrons, it has 2 in its inner shell, and then it has 8 out here, 7 out here. And if it could gain that 1 electron, then it would feel like a noble gas. But then that would make it negative, because now it would have 10 electrons, but only 9 protons. So the fluorine would be minus 1. Okay? And they can gain up to 2 or 3 or 4 electrons. They can even give away 2 or 3 or 4. So these numbers can change, and based on the numbers, how many electrons they have either lost or gained. Okay? So an ion is a charged atom that has changed the electrons in its valence shell. The number of electrons it changes is the size of the number of the charge in the upper right-hand corner. So when we have our isotope symbols, we can add this little thing. So we have the atomic number down here, the mass number up here, but we can also have a charge number here based on its ion state. Okay? So we got to be careful here. I want to make one last thing. We get confused because when we think gain, you gain something, it's this and that, but you got to be careful. When you gain electrons, you're negative, because what happens is your electrons are greater than your protons. And so you have more in number, so your charge overall is negative because you got more negative charge. When you're positive, you got greater number of protons than you do electrons. Okay? And so that's how something becomes positive. It gives away an electron. So this means to lose electrons. This means to gain electrons. So be careful when you're thinking that through. A neutral atom is an atom that hasn't gained or lost. So that means the electrons actually equal the protons, and so they neutralize each other, and there is no charge. Okay? So this would not be an ion. All right? So that's the basic idea behind isotopes and ions. Okay? And so we can put that kind of stuff information in there. Remember, we have symbols. They can be positive or negative. Okay? And we can have the little plus and minus signs. Here, oxygen has gained 2 electrons, so it's negative. Okay? But it's negative 2. And so why do they want to gain? Because they want to be like a noble gas, we told you a few minutes ago. Okay? And so we just want to make sure you understand the ideas between neutral, positive. Neutral means they're the same charge. Positive means that we have more protons, and here we have more electrons to make it negative. Okay? And so I just wanted to give you those concepts. Thank you very much for joining me. You have a great day.